Hello everyone. First of all, thanks to MIT Air for giving me the opportunity to show our work, and welcome to watch this video. As shown on this page, our job is named as Skull-RCNN, and the authors are from the Huazhong University of Science and Technology and Wuhan Union Hospital. This video will follow the main framework of our paper. Skull fractures following head trauma may bring several complications and cause epidural hematomas. Therefore, it is of great significance to locate the fractures in time. However, it is not an easy task. As shown in the two CT slices, the fractures usually present as narrow slits. The locations and the lengths of fractures are diverse. And the statistics of annotated boxes in the collected data shows that a considerable percentage of the fractures have very small sizes. All this make the previous method could not achieve a high accuracy. So, based on the fast RCNN, we propose the Skull-RCNN. Different from the previous one, the learning-based region proposal network is replaced by the skeleton-based region proposal method, and the full resolution feature network is put forward to be the backbone. Next, we will introduce these two methods in detail. When you see the CT slice, the first feeling may be that this image is somewhat empty. The useful information is just the white parts, skull. So, RPN generates the candidate boxes on the image even is not proper. We discover that a simple principle is that the skull fractures only distribute on the skull. Thus, as you can see, based on the region image directly, we first obtain the skeleton of the skull, and all the candidate boxes are generated over the skeleton. It compromises in lab boxes containing the fractures with less candidates. In fast RCNN, all the candidate boxes share the same feature maps. Then some researchers propose the EpiN. Boxes with different sizes are estimated by different feature maps. This is because for the small boxes, local information is very important, which is losing in the high-level feature maps. However, in EpiN, the output feature maps cannot achieve the same size of the region image, so the local information is still defectiveless. To get more accurate local information for the small fractures, we introduced the framework of some segmentation networks, a classical encoder-decoder architecture. The encoder extracts the global information, and the skip connections with decoder keep the local information. The highest resolution of the output feature maps is the same as the origin image. Come to the experiments. 45 CT scans are collected. From the table, the performance of Skull-RCNN with EpiN is between the other two models. Demonstrate that both the two proposed modifications are valid. And of course, the inference time of the Skull-RCNN is much less than the fast RCNN. An interesting fact is that the APs of the small fractures are all higher than the APs of the whole validation test set. This is because that most of the fractures are smaller than 16 × 16, and the structure of the multi-level feature network EpiN and the full resolution feature network are trained separately for the boxes with different sizes. So, the detection performance for the larger boxes are worse than the smaller on the contrary. Here are some subjective results. The green boxes are true positives, the red boxes are false positives, and the blue boxes are false negatives. The biggest constraints on performance is that some lumbar sutures are also detected as fractures. Thank you for listening.